So good morning my dear students. I welcome you to NEET World. So today we will be discussing the PYQs of JEE, NEET and EAPCET. So the first question here is from JEE. Here we have the given substrate is treated with HBr so that we are going to get a major product A. So try to identify this A from the given four options. So look at this. This is a very easy question, but it involves a rearrangement reaction here. So what is the reagent given here? HBr, right? So how it will be added? Tell me. HBr is a strong acid, right now? So it will be dissociates. So it will be dissociates like H plus and Br minus. So now this H plus is the electrophile involved in this reaction. So where it will be added here, see we have a double bond here now. So these are the carbon sites involving in the reaction. So this carbon double bond will take this H plus, so that we will get something like this. See, carbon and this side is methyl group and here you have CH2 group. Now we are adding hydrogen. So I am adding hydrogen here so that see the pi bond is shifting towards this carbon. It means this carbon is losing the pi electrons. It means this carbon should be placed with one positive charge now. Yes or no? Why? Because the pi electrons here is given towards H plus, so that this carbon is losing the electrons. So I am writing positive charge on it. So now here carbon, what is the degree of this carbon? See, one carbon, second carbon, three carbons are surrounded by this carbocation. I can say this is a tertiary carbocation. Okay. So now here you can also think how many carbons are involved in the ring? 4 carbons. Okay. So actually carbon having sp3 hybridized. Like if I say methane, what is hybridization of carbon? sp3, right? So what is the bond angle here? We know 109.5 degrees we are saying. Okay, but if you see all these carbons are sp3, but they are having in a square, what is the angle here? 90 degrees, right now, but actually it should contain what? 109, but it is having only 90, therefore it makes it to be more strain. Okay, therefore ring expansion takes place. See, the bond will shift from here to here, something like, see now this bond is shifting from this carbon to this carbon, so that the number of carbons in the ring is becoming more now. Ring expansion is taking place. So 4-member ring becoming 5-member ring by shifting. So now let us number it 1, 2, 3, 4, 5. Like that we will get. Okay. So now let us write a 5-member ring. Okay. So this is the first carbon. This is the first carbon if I say. Okay. So now this is the first carbon here. And to this we have one methyl group this side and one more methyl group this side. Okay, this is the first carbon I am saying, and this is second, third, 4 and 5. See, between 5 and 1 a new bond is formed. This is a new bond formed between 5 and 1. Okay, so now which carbon is losing that sigma electrons? See, second carbon is getting disconnected by the bond. So it means on carbon number 2 you should put a positive charge. Okay, so now this is secondary carbon. Okay, now what happens is one of the methyl group from here to here rearranges takes place. Okay, why it is shifting? See, this is a secondary carbon. So after shifting you are going to get a CH3 group here and one more CH3 here. See, from here to here one methyl group is shifting. It means the bonded electrons are shifting here. It means this carbon should get now positive charge. So out of these two carbocations, which is more stable? This is a carbon having one carbon attached, 2 carbons. It means secondary carbon. This is a carbon attached 1, 2, 3. It means 3-degree carbocation. Which is more stable carbocation stability? 3-degree carbocation is more stable than 2-degree, right now. So that's why rearrangement is again taking place like this. So now finally out of HBr we have added H plus. Now finally we have Br minus as our nucleophile attacks here, and you will get a product something like this. CH3 already there, here Br, that's it. This will be your major product. Okay, so look at the option. Where do we have? Option D. Okay, so our option D will be a perfect answer for this question. Okay, now I will be giving you one more simple question here. Same expansion of rearrangement reaction involvement will be present in this. So try to do this. So just take it like this. Okay, so I have double bond here. I am just saying you to add HBr. So where do we need to add HBr? Tell me. Where do we require to add HBr? What is the reactive site here? Double bond is here only now. It means to these carbons, any of this carbon will taking that H place. Okay, so now out of these, see, if I add here on this carbon, if I add, we will get a hydrogen here and a positive charge here. Okay, now instead of adding here, if I add here, we will get a hydrogen here and CH2 plus here, right now. So this is a secondary carbocation, this is a primary carbocation. Which is more stable? Secondary, 3 degree, 2 degree, 1 degree. Just remember, this is the carbocation stability order. So if this is stable, so if it is stable, this will be forms as major, right now. So when we add HBr, always add H to the terminal one and he make a positive charge on the internal carbon, so that we will get a tertiary or secondary carbocation. Now after forming this, see, if I shift one hydrogen from here to here, what happens? See, here we have methyl group, from here I am shifting hydrogen to this position. So this carbon should get now positive charge. Why? We are shifting this hydrogen from here to here. Okay, so here hydride shift, I can say hydride shift. Okay, or carbocation rearrangement you can say. Okay, now tell me, this is secondary, this is a tertiary, which is more stable? Tertiary is more stable. That's why this rearrangement takes place. After this, what we need to do? We need to add this bromide ion. Okay, so it will be added on this carbon, you will get something like this. This will be your major product. Is this clear? Yeah. So now one more reaction for your practicing purpose I am giving you. So just take this in your notes and try to solve this. Okay, so simple, I am putting a double bond here. Okay, so what you need to do, tell me, HBr I am giving. Again, whatever I discussed till now, all these reactions are rearrangement reactions only. Okay, you just try to solve this question, where do we need to add H plus? Remove this side, so add H plus here, create positive charge here, it is a secondary. So from here I can shift a proton to this position, like hydrate to this position, we will get a positive charge here, add bromine here. So what is your final product? Okay, it seems to be difficult, but if you practice, it will be easy. This will be your major product. How you will get, again think once again. So first add H plus to this position, carbon. Okay, so after that you will get positive charge here, which is a secondary. Okay, from here you shift hydride from here to here, therefore positive charge is shifted over here, carbocation rearrangement. Why I am shifting here? The carbocation here is more stabilized by this benzene ring pi electrons. I can say benzyl carbocation it is. Okay, so now here if we have carbocation, then this bromide ion will come and attack them. That will be your final product here, major. Okay, like this you should decide the answer. Okay, next. Look at this, one more question here I have. See, to this cyclohexene we need to add chlorine. Okay, so where this chlorination takes place? There are two types of reactions in presence of sunlight and directly in CCl for non-polar solvent. So what is your answer here, tell me? So whenever you are doing this reaction, chlorination in presence of sunlight, you have to do the reaction at these positions. What is these positions called? These are called allylic positions. What is that? Allylic position. It means double bond, adjacent carbons are there now, those are called allylic carbons. Okay, so how many allylic carbons are there? This one and this one. So it means I need to add one chlorine here and another chlorine here. So that what is our final product now? Chlorine here, that's it. So this will be our A. Okay, so similarly you tell me for B, what happens in B is when you are doing reaction with CCl4, it follows halonium ion mechanism. What is that? Halonium ion mechanism. What is this halonium ion? So wherever you have double bond, so take here separately I am writing. Okay, so double bond here we have now, so chlorine, chlorine. So what happens is So lone pair electrons here, lone pair electrons here. See, the pi electrons will be shifted here, this bond will disconnected, and it will be forming a ring, a cyclic ring like this. Okay, so chlorine, chlorine like this, and we have one more chloride ion, this one. So this will attach either here or here. Just add here, and it will be opens. So that we will get chlorine here and one more chlorine here. Simple. If the reaction chlorination is taking place in non-polar solvent like CCl4, just remove the double bond, put chlorine atom on the 2 carbon atoms wherever we have double bond. Again, if chlorination is taking place in presence of sunlight, what to do? The adjacent carbons are there now. So on that carbon you put one chlorine atom, that's it. Okay, simple. Okay, now I will be giving, so which option is correct out of this 4? Fourth option D will be a perfect answer. Now look at this. Look at this, a simple one I am representing here. Okay, do not scare by looking at the structure. So I am putting a double bond here. I am saying you to do chlorination in presence of sunlight. Tell me where I should do. This double bond. Whenever you have sunlight, what I told you? Allylic position. Yeah. So where do we have allylic position means? This is the site, right now. So what I should do? Right remaining as it is, you put one chlorine here, that's it. That's it. This will be your answer. Is that clear? Yeah. So now if the same reaction if I want to do in CCl4, what is your answer? The same reaction I want in CCl4, just now we discussed above. What to do I told you? Just remove the double bond and next place one chlorine on one carbon, another chlorine on other carbon of the double bond. That's it. Simple only now? Yeah. Okay? Yeah. Next thing is, yeah, this is from redox reaction. Try to answer this question. So tell me answer for this. Read the question. Number of moles of ferrous oxalate oxidized by 1 mole of KMnO4 in acidic medium. So just simple it is. Even we will do one experimental reaction later, hands-on demonstration we will do later. But as of now you see, what is this? FeC2. So ferrous oxalate, FeC2, oxalate means C2O4. Okay, so it will be -2, this will be +2. So ferrous oxalate means this is the formula. So whenever you treat this with KMnO4, KMnO4 in what medium? In acidic medium. Okay, in acidic medium. So what happens here? So here iron is there now. So KMnO4 is a strong oxidizing agent. If it is an oxidizing agent, this will be considered as reducing agent. Why? Because oxidizing agent means it will oxidize others, reduces itself. So whenever you are doing this reaction in KMnO4 in acidic medium, so manganese will convert into Mn+2 form. Okay, whereas iron is there now here, iron will be converts into Fe+3. It means manganese is undergoing reduction, iron is undergoing oxidation from +2 to +3, and C2O4 2- is there now. So here carbon is in +3, converts into carbon dioxide like CO2. So carbon here oxidation state is +4. Okay, like this we need to do. See what I am saying, oxidizing agent is that species which oxidizes others, reduces itself. See +7 is converting into +2, it means undergoing reduction now. So like that. Okay, so how to do this question? Very simple here. Just use N into N factor of oxidizing agent. Okay, that is nothing but number of gram equivalents of oxidizing agent equals to number of gram equivalents of reducing agent. That's it. Very simple. Okay, yeah. So now look at here. KMnO4 is our oxidizing agent now. So how many moles they given? Oxidized by 1 mole of KMnO4. So how many moles KMnO4? 1 mole. And what is its N factor? N factor means +7 is converting into +2 now. How many electrons involved in that? 7 to 2 means 5 electrons gained. So N factor here is 5. Okay, so 5 here you take. And this side reducing agent means this one, iron +2 converting into +3. So, and carbon also converting into +4. So, this is completely undergoing oxidation now. So, the N factor involved, total N factor involved here in this process is how much? So, for iron is 1, and for carbons, how many carbons are there? 2 carbons, each one is 1 electron. So, +3 to +4 means 1 electron. Total how many? 2 plus 1, 3 I can write. So, N factor of this reducing agent is how much? 3. Okay, and they are asking number of moles of ferrous oxalate. So, this is what you need to find here, N. So, except N you have everything now. So, your answer is N equals to number of moles of ferrous oxalate is 5/3, that's it. This will be your answer. So, do we have, yeah, option number D will be our answer for this question, right now? Clear or not? Yeah, next. Will you do one question if I give? Can take this. So, number of moles of oxalic acid or oxalate ion is oxidized by 2 moles of MnO4 minus in acidic medium. Okay. So, same concept you need to use. Oxalate means instead of taking ferrous oxalate, I have just taken oxalate. It means C2O4 minus 2 only I have taken. Okay. So, otherwise they will say something like sodium oxalate like Na2 or calcium oxalate, something like that. Okay. So, here this won't involve in the reaction, only oxalate ions will be involved. So, what is the N factor in that case you find? So, what is the N factor you will get here? 2 carbons, not 2. So, 1 carbon plus 3 converts into CO2 plus 4. It means what is the number changed here? 3 to 4 means 1 electron. Okay. For each carbon 1 electron. How many carbons are there? 2 carbon. So, 2 into 1 means 2. N factor will be 2 for oxalate. Similarly, you do it for manganese, that is +7 to +5 plus 2 means 5 here, that's it. So, 2 into 5 for manganese equals to 2 into N, that will be. So, answer will be 5 you will be getting. Just try, okay. If not, you can ask me, I will explain in detail. Almost I given the answer also. Next, what about this? How many bridging oxygen atoms are present in P4O10? Okay, if you look at the molecule, it looks big, but let us write the structure. See, phosphorus, simple it is, phosphorus, let us put. Okay. So, now satisfy the valency of this phosphorus by placing oxygen atoms in between them first, like this I have kept. Okay. After this, I am inserting 1 oxygen on each of this phosphorus. Okay. How many over? 8 over. Okay. So, 9, 10. So, this will be the structure of this P4O10. Now, how many bridging oxygen atoms are present in the molecule? Bridging, POP bridges, oxygen atoms. See, this is one bridge like POP bonds they are asking. How many POP are there? So, 1, 2, 3, 4, 5, 6. So, POP bonds are 6. Like this they will ask. How many PO bonds are there in P4O10? PO 1, 2, 3, 4, like that they will ask. Okay. So, simple now. See, PO bonds are 4, just you need to count. Okay. So, now similar question I just want to ask you for P4O8. If they ask for P4O8, you just simple remove 2 P double bond O bonds, that's it. It means number of POP bonds will be same, but PO bonds will be 2 only, because 2 will be removed when I say P4O8. Okay. If I say P4O6, here also number of POP bonds will be same, just remove this. How many oxygens are less in this case? P4O6 means here 10 are there, here I am saying 6. So, 4 are less now. So, remove all these PO double bonds, you remove. PO double bonds will be 0, POP bonds will be 6. Like that you should do. Okay. Okay, next. Look at this. This is from coordination complexes. How you will answer? Just try that. Yeah, tell me. Identify the complex ion with electronic configuration T2G3 Eg2. So how can we do that? T2G3 Eg2 means, first of all you need to know the crystal field theory. So Fe, in that just look at this. First I will tell you for one compound, you can able to do for others. Okay. So what is the central atom here? Iron. What is the oxidation state? See, these are neutral ligands, so oxidation state will be +3. Whatever the charge present on the complex, that will be the oxidation state of that atom if the ligands are neutral. Okay. So now it means iron atomic number is 26. Okay. Okay. So from the 26 you are removing 3 electrons. See, if it is iron atom, you should write 26 electrons means simple. See 26 now, so you just write 3d6 4s2. Okay, 26 means, see, 6 you put on D, 2 on SU, like that you can remember. Okay. Now +3 means how many electrons you should remove? 3 electrons. So that 2 from here, 1 from here, it will become 3d5 4s0. Right now? After this you just represent them in the orbital representation. 1, 2, 3, 4. Okay, I mean 5 orbitals are there here, and this is s orbital. This is 3d. This is 4s. Okay. Next. Okay. So now this is 4s. Now 4s orbital, do we have any electrons? No. So can I erase this? Yes, I am erasing this now. Okay. We have only d orbitals. How many are there electrons in d? 5. 1, 2, 3, 4, 5. Okay. So now these d orbitals, when we place them in the ligand field, what happens is the degeneracies will be lifted and they will be splitting into 2 equal energy levels. I am writing it 1, 2, 3, 4, 5. Okay. So this will be splits into 2 energy levels. One is called T2G set, another one is EG set in octahedral. Okay. Okay. So now tell me, what is the nature of water? Weak field ligands or strong field ligand? Water is a weak field ligand. H2O is a weak field ligand. Therefore, you need to fill the electron. See, if it is a weak field ligand, see, the name itself saying weak field, the splitting will be very weak. Okay, energy gap will be less here. So 1, 2, 3. If weak field ligand, just fill the electrons as like free metal, like this only. 4, 5. So what is that? This is T2G set now. So T2G, how many are there? 3. And EG? 2. So this is satisfying the first one. Okay. Now can you do it for second one? Chromium +3. Okay. So chromium +3, it means what is the electronic configuration? Chromium atomic number 24. So 24 means you should write 3d5 4s1. Okay. So but removing 3 electrons become 3d 4s0 3d3. Okay. So we have only 3 electrons, that will be in T2G level. Do we have any electron EG? No. So not, this is not the one. First one we got it as correct. I am just verifying other options. So nickel here, what is the atomic number? Nickel +2 D8. It means 28 now. So it means what you should write? What you should write here? 3d8 4s0. Means +2 means you remove the 2 electrons here. So D8 means just fill the number of electrons. Again we have weak field ligand. So 8 means 5 over next 6th, 7th, 8th. It becoming T2G6 EG2. Okay. But we required only T2G3 EG2. So which is perfect answer? Only first one. Okay. No other options are having the same configuration. Is that clear? Okay, now tell me, will you try for T2, this titanium complex? Titanium atomic number? Scandium, titanium, 22. So 22 means plus 3 is there. So remove 3 electrons. 22 means T2, D2, S2. Okay, so if you remove 3 electrons, it becomes D1 electron. Only 1 electron is there in d orbital, so we won't get this electronic configuration. You will just get T2G1, that's it. Okay, so similar manner, will you try this question? Which are the following will have spin only magnetic moment of 2.86. So in order to have 2.86, okay, what is the magnetic moment formula? Root over n into n plus 2 Bohr magnetons. Okay, so this is a formula to find magnetic moment. So if you have n value 2, then your magnetic moment will be 2.86. Okay, so it means how many unpaired electrons are required? 2 unpaired electrons are required. So now you need to write their electronic configuration, okay, in the respect to hybridized compounds, and those are compound which is having 2 unpaired electrons will be your answer. Now first case you tell me, cobalt plus 3 it is having oxidation state. So it is 3d6. So 3d6 means 3d6 4s 0. 1 2 3 4 5 1 2 3 4 5 we have. Okay, this is a weak field ligand, so electronic configuration as it is. Number of 6 means like this. Okay, how many unpaired electrons are there? So n value is 4. So but what we required? 2. So this is incorrect, like that. So if you do it for this one, same cobalt only plus 3, but here ammonia is a strong field ligand in the case of cobalt plus 3. Okay, so that electrons, if you feel like this is the scenario in case of weak field ligand, but in case of strong field ligand what happens is these electrons will pair up. Okay, so like this it will become. So do we have any unpaired electrons? No, this is diamagnetic, so this is also incorrect. Now next nickel plus 2 here. So nickel plus 2. Okay, so what happens here? 8 electrons are there, plus 2 means 1 2 3 4 5 6 7 8. So how many unpaired electrons are there?
2.
So 2. So this will be our answer, that's it. Okay, like this you should do this. Okay, next, correct order of reducing ability of the following hydrides. So which hydride is strong reducing agent, they will ask me. Okay, they will be asking. See, nickel, nitrogen, like ammonia we have hydride of nitrogen. So these are 15th group hydride: phosphorus, arsenic, antimony, okay, bismuth. These are the elements and respect to hydrides. Okay, so now down the group, what happens to the size? Size of elements increases. So nitrogen to phosphorus, phosphorus to arsenic, like that size increases. So if size increases, what about hydrogen size? Same. In all the case, hydrogen atom size is same. So if they have similar sizes, small size means the overlapping will be very strong. So bond will be very strong here. But as we go down, what happens? Big atom and small hydrogen atom. So overlapping will be very weak, so which will be breaking the bond easily. So in the last case, bond breaking is easy because of poor bond. Okay, therefore poor overlapping. So this can be strong reducing agent because easily give hydride. So down the group reducing nature increases. So it means bismuth hydride is greater than this. So for least one is for ammonia. So here we have. So out of that, what I told you, down the group stability decreases, so that will be your answer. Okay, yeah. Next, this one again, yeah, try it. So look at this, given compound substrate is treated with alcoholic KOH. So whenever you have alcoholic KOH, if it is aqueous KOH, substitution reaction takes place. Whenever you have alcoholic KOH, elimination reaction takes place. So where elimination takes place, this is already in the conjugation with the ring electron, so it won't goes out. Only this can be possible now. Okay, here you have alpha, beta, like this is alpha carbon, this is beta carbon now to the bromine. So the hydrogen from beta position and bromine from here will be removed as elimination, like OH minus will take this proton, so that we will get bromine here as it is, like this. Okay, what is this? This is our B. So B is treated with what? HBr. So I told you how to add HBr in the first 2-3 reactions. I told you first add H to the H plus to the double bond. Where to add? This side or this side? This A, B side or A side? Where I should add H? If I add A here, we will get a carbocation here, which is secondary. If I add H here, we will get carbocation here, that is primary. Which is more stable? Carbocation at secondary position is more stable. So that it means you add H here, carbocation generate carbocation here. Okay, so that we will get a H here, carbocation here. Right now this is more stable. After this we have bromine, so add it here, that's it. There is no other possibility for rearrangement here. No need to worry about rearrangement here. Okay, that's it. This will be our product. So where do we have like this? Which options? A is something like, B is something like this, C and this one. So we have C option with this answer. And what about their nature? How these are different? A and B. I mean this A is there now. This is starting material A and final C. How they related? See, both of them have same molecular formula, but position of bromine is different. Position of Br is here in the first case, terminal case, here in the inner side. So I can say they are differ in the position of bromine, so positional isomers. So perfect answer for this will be C. Okay, is that clear? Right. Next thing is, yeah. So yeah, try this question. Schwarz reaction means there are some basic named reactions. We have something like Finkelstein reaction or Schwarz reaction, okay, and Woods reaction, okay, like these kind of names are there. So whenever you listen the word Finkelstein reaction, this is for preparation of alkyl iodides. Remember this, what is that? Alkyl iodides are prepared by Finkelstein reaction, and Schwarz reaction is for preparation of alkyl fluorides. Alkyl fluorides. Where do we have alkyl fluoride as a product? Fluorine. In which option? See, this is iodine is there, so this is what? Finkelstein reaction. They are asking for Schwarz. So if you look at this, what is this? Alkyl fluoride. Okay, so what is the name of this reaction? Schwarz. So for this, D will be a perfect answer. Now if I say Woods reaction means for preparation of higher alkanes from lower alkanes, like alkyl bromides to alkanes, okay, using sodium in dry ether. Okay, so this kind of reaction you have this one. So what is our B now? B is Woods reaction. Okay, like this. Even C also, see, sodium is used, dry ether is used. What is the name of the reaction? Same, Woods reaction. Okay, yeah, so same. So Schwarz reaction means what I told you, for preparation of fluorides. So which option it is? C2. Finkelstein means iodides. Okay, alkyl iodides. B1. Next, Sandemeyer reaction means this is for preparation of aryl bromides. Okay, A3. Next, B1 and C2. So C2 here. So only this option is there. So option D will be your answer. Okay, like this you need to solve the questions. Okay, yeah. So this is about the session, and these are the questions for practice purpose. Okay, so just give a try for solving these questions. Yeah, so this question I have discussed in the last class. So give a try. If you are unable to solve, just watch my previous live session, yesterday's live session. You can watch. These are the PYQs discussed in the previous live session. This is JEE advanced question. Just give a try. Very easy. If unable to solve, you just go and watch my previous live session, yesterday's live. Okay, all these questions are simple and important. Okay, just try these questions. Yeah guys. So if you are unable to solve this, just watch my previous, yesterday's live session from the playlist of this particular channel. Okay, and if you have any doubt, feel free to write in the comment box. Okay, we'll address them. Okay, if you are interested, you can join our Telegram group for taking our lecture notes and also to be connected with us. And you can post your doubts in the Telegram groups. You can join the Telegram group by clicking the link given in the description box. Thank you.